Well, I guess I'll go ahead. Is there any questions on homework 1 yet? Or if not, don't worry about it. I can answer those as time goes by. Um, okay, so if you go in, there's 2 ways you can go in. Most people I've heard to go this mastering assignments, and it takes you to the page. Oh, mine took me to the page with the calendar. Okay, so now I'm going to get rid of these things and see if it does that again. Does yours go to a calendar straight off, or does it not? So mine's got a calendar up there now. But you don't have to use the calendar. You can basically click here. But what I did, okay, the green means it's available. And so homework 1 is green and it's available. And there is a due date, but I'm not taking off. But what I did is I went ahead and made homework 2 available, just in case you wanted to start ahead. So just go do those. There's quite a number of problems this time. There's not as many next time. And there's 3 types, or is there 4 types? We have something called coaching activities, tutorials, which kind of to me are the same, and the end of section problems. And then there was one other type, and I can't remember what that other type was. So just go do those. Did anybody have a question on any of them right now? I mean, if you don't, you can delay and ask it on Wednesday. That's fine with me, or Friday or whatever. I'm sorry I had to bail on you Friday because I volunteered, and then I thought I was supposed to be there at 4, and at that point I realized I was supposed to be there much earlier, so I had to leave early. So let's go. If we have no questions, I cut it down. Let's go to the book, and after it comes up, they have better pictures than I can draw, which is why I would do. So they've got this concept of a regular vector in space. So here it is. Just the regular blue part is the vector itself, right here, and then you've got the different components of it. So if you wanted to list this, and I don't know why I'm doing it because I could just scroll down the screen, it's just AXI plus AYJ plus AZK. And so you have the X component goes here, and then the Y component and the Z component. I'm not a great artist, but if I took those vertical, and this one already is vertical, and I took this line and did it, and then let's see if I can do that line. I think I can do. I think I can. And then this one. So in other words, it forms a box in which I mean, he already drew the one side of the box. Here's the one side. And then, so if you look at this thing, it becomes a box. So there's your box. And there's a vector in the middle of the box pointing from one edge, one vertex of the box, directly across to the other. And so essentially that's all this is breaking it into a box. Although he rarely draws the box around it, but sometimes it's useful to think of that way. So all you're doing is copying this vector to there, this vector to here, this to there, and this to here, and you'll end up with a box. Now the question is, how do you determine AX, AY, and AZ given some information? And we'll scroll down and we'll look at that. Oh, my shoe came untied. Hang on a second. I don't want to fall in the middle of it. I thought I tied it pretty well, but I have to use a pair of vice grips or something to tie my shoes. So here. Hello. So here he's got this thing set up. So he's got what we're talking about, this equation 2,3 is what we're talking about. I don't know if it's large enough for you to see, but that's AXI, AYJ, and AZK. And he has the IJK pointing out there. Nothing new to you. I mean, you should have gotten some of that in physics. The IJ and K. For some reason, the keyboard's not attached to that. So then he comes down, he says, okay, yeah. This is the I direction, that's the J direction, that's the K direction. So all I have to do to find this vector, really realize that these are length vectors of 1. And so you just multiply AY times J, AXI. And nothing is, so you should have seen that somewhere before. And then you got the magnitude. Magnitude is just the square root of the squares of all of them, all added up. Now he's got an interesting drawing, and this is the prelude to determining some more information. He's got a flat part of the triangle here, and he's got a part here. This triangle is in vertical space, and this is in the ground space. You can notice he has a 90-degree symbol here. And then he says something about coordinate, direction, angles. Now, we started talking the other day, I'm not sure, let's see, how much of this space, the thing's not on. Trying to see if that works. Huh. That's weird, this whole thing. Okay, hang on, let me look at make sure that so why did the camera do that? Okay. I don't know. The camera's at a slightly different point. When it comes down, it focuses on the back of the projector instead of the board. So I've got to try to figure out how to, I don't know. It's like managing monkeys that have squirrels as pets. That's kind of what I feel like my job is sometimes. So, we talked about this at one point. A dot B is equal to the magnitude of A, magnitude of B, and the cosine of the angle between the vector A and B. So you could have, remember we did one where it was a 4I plus 3J, and then we did another one that was 3I plus 4J or something. And we basically did this out. And, I kind of described that a little bit did I do that? Where we were talking about, you're used to doing I'm trying to make sure I did it in this class and not dynamics, where we said you're used to doing sine of an angle and cosine of an angle, and we were talking about that. So I think it was in this class. So let's take a look at this in the context of that. And now, since we already have A, I'm going to use A, but I'm going to replace B with, say, the I vector. Cosine of the angle between A and I. And there's a name for this one. We'll find this out in a minute. So it turns out, if you took the A vector, the A vector can be written as AXI plus AYJ plus AZK. So that is the vector that's written, that's this vector. So it can be put right here. Now, one of the things that happens is if I put this, there are two components to think of. There's this side, and then there's this side. So let's focus on this side for a moment. And in that, we'll say A dot I, is equal to A, which is AXI plus AYJ plus AZK dotted with I. because that's what you're doing. Turns out this will yield you 1. This and this both equal 0. Why is that? Because if you break this down, what you'll find is this: ax I dot I plus ay j dot I plus, now multiplying each one of these terms, and then az k dot I. Now if I focus in on this and look at this equation, then I dot I will need nothing more than the length of I and the length of I and the cosine of 0, because 0 is the angle between I and itself. And this is 1, and that's 1, and that's 1, so it's all equal 1. But if you do I dot j or I dot k, you'll get I, length of j, or k, you could do k, and the cosine of, they're all 90 degrees. And since they're all 90 degrees, it becomes 0. So then if you look at this, the response to this is a dot I is equal to nothing more than ax. So let's think about this. Let's look at the left. We're looking at the left side right now. We're saying, we dot these, dot it with I. The only one left is this. This is left as 1. This is 0. And that is 0. So all I've got left is that. On the left-hand side of this, I've got that. On the right-hand side, so this is what I've got on the left-hand side. What do I have on the right-hand side? Here, I'll tell you what. Let me get rid of that for right now. On the right-hand side, I have the length of A. The length of I already know that. That's just 1. Cosine of the angle between A and I. And what we're going to look at in a minute is we're going to stare at this. Okay, so this forms an equation here. And we're going to look at a new parameter here. They call it alpha here. Now, he says coordinate direction angles. So let's roll up and look at this. And we'll see that instead of you just being given these things, I'm trying to give you a basis of understanding here. So the angle between A and I, between A and this vector I, is alpha. The angle between the vector A and the J is beta. And the angle between A and K, the vector, the angle between this vector and a vector going straight north is gamma. And okay, so his gammas don't have, my gammas have a little loop on the bottom. So if you look at it in the book, and depending on the typeset you're using, sometimes you'll find that some books typeset this with a gap in the bottom. Mine's going to have a gap in the bottom, if that's okay. So now we've got this. So now let's look at this and let's break it down. I'll move it up, or maybe this, since we've done this, I'll move this whole thing up and do all 3 dot products. In other words, A dotted with I is nothing more than AX, and it's equal to the magnitude of A times the cosine. Now I'm using another symbol. I'm using that symbol right there, the alpha. But if I dot A with J, guess what I get? I get the Y component. It's nothing more than that, cosine of beta. Why? Because beta is the angle between a vector that shoots up that way and this blue vector. And then A dot K is nothing more than A in the Z direction, magnitude of A, cosine of the gamma. That's my. So in fact, this, okay, you'll see these equations in a minute. And he just puts them on the page and says, here, just accept that. That's what that is. But to me, you're going to have to know dot products eventually, so you might as well try to find out why these equations are just pooped on the page. They're not. They come from this, and they come through this. Now, he won't put this part on the page. And so what we'll do is we'll go down a little bit lower. And so suddenly, there they are. They're just thrown on the page. Cosine of alpha is equal to that. Cosine of beta is equal to that. So then he says, determine and consider the projection of beta referring to the shaded triangles of the figure. We have that. And you're like, okay, I guess I just got to accept that. No, this is where they came from. So let's look at each one of these. What happened here? Okay, this is a little bit weird, but he's saying cosine of alpha is equal to ax over the magnitude of the vector a. He does not, he should, but he does not put that on the bottom. If you look, it's kind of hard to tell. It's really subtle. And, okay, maybe it's not as subtle as I thought because it's not even there. Usually, he makes the dark be the vector, but anyway, a is the length of that vector. And likewise, you can see where the cosine of beta is equal to ay, move this underneath, az, move that underneath, and you get a relationship. So this didn't just appear out of thin air. This comes directly from the definition of a dot product. And this thing right here is way more powerful than you can ever imagine. And I will use it at times in context that you'll be looking at it, you'll be thinking about stuff. For example, this is in dynamics, not in this course, but there are often mechanisms. Let me just draw one, for example. And a mechanism might look like that. And what you're supposed to do is you're supposed to come up with a triangle out of this, in which you're supposed to come up with a distance d1 that's from here to here, and a distance d2 that's from here to here. Turns out you can do some dot products. So in the text in dynamics, he solves this in a particular way. The way he does it, he says, oh, here's an angle, and you're doing a bunch of trig. Turns out if you do a couple of dot products, you can solve the distances really easy and really quick. So this is a tool that is way more powerful than it's being used. And that's just one case. And when you get into dynamics, you have to wait. When you're in dynamics, you have to wait like a month to a month and a half before I get there. This just takes time. So, this being the case, okay, these are the relationships. Now you have some idea that where they actually showed up, and what he does do a really good job here is the graphics here that gets you an idea that, okay, this is a triangle leaning over in space there. It's not vertical, it's leaning over, and it's kind of tilting out towards us, and this is an angle between these two. What you find out is, okay, wait a minute. Is there a relationship between alpha, beta, and gamma? Well, actually there is, okay? And if you really look at it, let's look at it like this. Okay, I can write this vector A is equal to AX I, give me a second, A Y J plus A Z K. So I can write that vector that way. We already know that. We also know the length of it is AX squared plus, hang on, AY squared plus AZ squared. So we know that. Well, now, let's think about this for a minute. This is nothing more than the length of A, right? Now let's monkey with this and that and all these together to come up with something interesting. AX that could be put in here is nothing more than this A which is dot, times dot. Okay, so I'm going to write it out completely. Just bear with me as I do this. Maybe, well, okay, so let me write it in 2 steps. Okay, so as I write it in 2 steps, K, that's supposed to be K. So I write this thing in 2 steps. The first step is that. So all I'm doing is I'm taking this AX, which is this, inserting it into here, take the AY, insert it in here. Now, something really interesting here. Let's do this. One of the things we can do is we can do this. So instead of rewriting the equation, I'm just doing that. Okay, so now I got this new vector that's over here, and what I'm going to say about this vector is this vector right here is this. If I took a vector and this thing is 10 long, so say this vector is 10 long, there's a new vector right down here, which I'll just call UA, which is a unit vector exactly in the direction of A. If it is a unit vector, what's its length? So what is the length of this vector? So in other words, let me give you a case in point. Here's a vector. This vector is A, or let's call it B. B is equal to 3I plus 4J. What's the length of that vector? So 3, 4, 5, right? Isn't that the length of? So the length of B is going to be equal to 5. So if I want a unit vector going in the direction of B, it's going to be 3/5 I plus 4/5 J. In other words, the unit vector that points in the direction of B is the B over the magnitude of itself. And now I've found this being 5. It's a 3, 4, 5, you know. It's actually, might not look this way, but it's 3, 4, and 5. There's your vector. So if I look at this vector and I say, now I want to take the unit, I want to know the length of this. If you don't believe me, pull out your calculators and do this. What is that value? It turns out that value is going to be 1 because you made it a unit vector. By the way, the unit vectors are going to invade your conscious a lot. They're all embedded in here. There's a lot of reasons that they are. So you've got a vector length 5. This is its components. You divide this, you get this out of it, and I want to check this, and its value is 1. So anytime you're looking for any unit vector of, say, some R, where it's some vector R over its own length, this becomes of length 1. So that means this is of length 1. So this is of length 1. These cancel. So now I have a vector that I'll just call it UA just because I need to have a symbol right now. So I'll call it UA, unit vector in the direction of A, is equal to cosine alpha I plus cosine of beta J plus cosine of gamma K. Did y'all catch that error I did? A beta and a beta, that's supposed to be gamma. So there you go. What's the length of that vector? The length of that vector is 1 because we made it 1. And it's also equal to cosine squared alpha plus cosine squared beta, beta plus cosine squared gamma. That is a relationship that ties alpha and beta and gamma together. So you can't just pick anything random. So you can't just say, oh, alpha looks like it's 60, beta looks like it's 30, and oh, I'll just make gamma equal 90. Go put these in this relationship and you may not get one. So in fact, what they do is, since the square root of this is this, you can just take the square root off, because there's got to be 1 under there, and they'll have a relationship like that. And the reason being is because of what I just said, and if you roll down a little bit further, you'll see that. Okay, so here's the unit vector. A is the vector A divided by its magnitude, the AX. And then he just says this is the relationship, which it is. I'll go up a little bit. This is what I got. So this, this right here is that equation. He goes one step further and he says, okay, now that I've determined a unit vector that goes exactly in the direction of A, I can find its length. Oh, its length is 1. And then he says, what are the components? That, and that, and that. So that ties this vector A together, this UA together. So, and what you find out is this is the relationship. Let's see, make sure I can get it to the point. Okay. So here's your relationship. This is how it's tied together. It's basically, this has to be satisfied. There may be problems in the book in which, or in the problem set, they may give you alpha and beta and no gamma. And you're like, how do I find gamma? I've got that question more. That is one of the most asked questions when you're looking at this. And you can't just pick a random gamma, but you can go over here and take this, these two, and you can say, if you're not given that, you would say gamma would equal to what? 1 minus cosine squared alpha, cosine squared alpha minus cosine squared beta. And then what you would do is you'd say, okay, that's cosine squared, right? So then you got to take square root of that thing, and then you got to uncosine it. So you basically move it over. He may have that down here a little bit. Maybe he doesn't. Maybe he just has it in the problem. And so there's a relationship between those two. Between those three, sorry. Okay, so that's one way these things are represented. And these are called, okay, so they all originated out of a dot product. And I'm going to leave it that way. And they're called direction cosines. Direction cosines. And they're basically alpha, beta, and gamma. He asked for this a fair amount on problems. So you might as well get used to it. But physically, that is more difficult to measure actually. So what is another way of coming up with these? And I'll show you something that happens right here, and that is, let me get this stuff out of the way, and then what will happen is more along the lines of something you might see. In other words, these are what I like to call projections. And projection mathematically comes all the way back to this. It comes back to the original definition, A and B. So here you got a different situation. Let's say this is a limb you have in your yard, or a tree that is broken down. I have one in my yard. I can bring the picture. So ice broke the tree down, and it sort of did like this. And so I went and sawed that off. So I still have this leaning branch that's about 10 foot tall. It's cedar, so I'm letting it kind of dry out. And then I'm going to cut it, take it over to a guy down the road from me and get him to turn it into lumber. But it's leaning over. And let's say it's high noon. So way up here, there's the sun way out here, millions and millions of miles away. So the sunlight is coming straight down. And when it does, it casts a shadow on the ground. So here's your shadow of your leaning tree or whatever. So there's your shadow of your leaning tree. Now, I may have to, you know what? I may have to redraw this and scroll down because, but anyway, so here's what he does next. Is he says, okay, what's the length of that shadow being cast upon the ground? Well, there's two ways you could do it. That length is the same as this length. Remember, it's a box. So the length of that, this length is the same. So if you're looking at that, you have to remember these are 90-degree triangles. So you look at this, that length is going to be the A, the length of A, the length of vector A, sine, I said sine, I wrote cosine, sorry. Sine of that angle, and that angle looks like that. So that's the length of this shadow. So I hope he reproduces this picture because now I got to scroll down. Okay, so now you have that happening there. You've established, okay, the sunlight is giving you the z coordinate. You have to decide how you're going to do your x and y. So somehow you put a thing on here so it's 90 degrees between these, and you have these axes on the ground. So now that you have this length of this shadow, what's the length of this? Okay, so AX is equal to, here's your angle, you're going to sweep through it to get there, you're going to say length of the shadow times cosine of that. So if you look at this triangle, the one that's in blue here on the ground, that's what you get. Now this length is the same as that length. So AY would be A of the shadow times sine of that thing. So you need just two angles, that one and this one. And suddenly you realize, okay, so if I were to go back and fill this in, AX would be, what's the length of the shadow? It's that. A times sine theta times cosine of that. Now y is equal to, I'm going to have to squish it back a little bit more. Sine. Okay, so here's my first one. Here's my second one. Now what's funny is AZ has no dependency on this angle at all. It's just the length up here, from here to here. You have this, you have this angle. And so it's nothing more than cosine of that angle. So now, a different arrangement, this is a little bit more palatable about measurements. If you had to come up with something here, you would have to know this, you have to know this, you have to know this. The other one, you have to know alpha, beta, and gamma. There is a third way we're going to come up with where you need to know no angles at all. And I'll show you that one probably next time. Maybe I'll get a chance to do it this time, I don't know. So how does he list this? Now let's scroll down now that I've done all that junk. And if I'm scrolling down, then this is just going to be in the way. And hopefully everything I said made some sense. But you have to realize the shadow length is this one. And that is what's put right here. And the shadow length is the same thing as that, which comes from the A sine of the angle right here. So let's go ahead and scroll down. I'll go ahead and move this out of the way. And so just like that, he does it. Now okay, it looks like I got this in the way. Oh, he reproduces the same drawing. Okay. So here's what he's doing. He's saying, here is my shadow length. My shadow length is that length. A sine of that, what we were talking about. And so here's my shadow length. Here's my shadow length. And I take that length and project it back over here, take that length and project it back over there. And I get my AX, my AY, and my AZ. So he did the AZ right off. I delayed and did it near the end. So again, you're looking at three unknowns. The length, some sort of lean over angle of your tree, and the angle you can look on the ground and measure. Here you have to have a protractor or whatever to get three angles. Here you only need two. Okay, so since we're here, I might as well do the third way, and I'm not sure he does it in this section, so I'm going to do it anyway. And let's see, or maybe I shouldn't do it. Maybe I should go on. Well, let me give you, okay, let me just lay it all out since I'm here. Let's say, let's give it some sort of physical meaning, so to speak. So let's say O is part of a boat in which there's a ring tied there. And now you've attached a rope right here. Okay. It is very easy. As a matter of fact, I can bring one in next time. You can get these laser measurements. You push a button, it shoots a laser, little dial right there tells you the distance from the back end of that thing to the wall. So it's easy to measure distances. You don't even have to have a ruler now. Now these devices are kind of expensive. I bought mine was $39 at Lowe's. I looked out there the other day and now it's like $160. I don't know why it went from $39 to $160. That's really baffling to me. And I'm not selling mine because I use it all the time. So measuring lengths is easy. So let's just say the guy went out here and he said, hey, give me this length and this length and this length. So how would he do it? Well, it kind of depends. Somewhere it would be like a dock here. Maybe it's a big block of concrete, or somehow he was able to get the measurement in the X direction, or say this way. He was able to get AX, AY, and AZ. So say maybe, I'm just going to make some numbers up. So maybe that's 10, maybe that's 12, and maybe that's 20. Okay. But that doesn't give me the unit vector. So how do we find the unit vector? Here's how we find the unit vector. Okay, so we got A is equal to 10I plus 12J. I'm making sure I'm copying it down right. 20K. So the unit vector pointing in the direction of A is 10I. Let's see, how do I do this so that I'm going to try to use photomath. So you know what? I'm going to do this. Okay, here we go. I'm going to make this thing kind of work for me here. 10 squared plus 12 squared plus 20 squared. So this is the one that's going to go in there. So I'm going to just, okay. So I'm trying to be, okay. So he goes through and he says this is, so what I'll do is I'll do this, 10 over length of A, I, plus 12 over length of A, J, plus 20 over length of A, K, which actually happens to be this. So it turns out UA is equal to 0.394, oh, come back to me. 394,055. Now I'm going to cheat. I'm going to do this and make photomath. Tell me what that is. It's not necessarily cheating, it's being efficient. 0.472866J plus, and now I just need to put this 20. And 0.78811K. So this is a new vector which points in the direction of the rope that I have. It's a unit vector in A, direction of A, and that's it. Now, can I get alpha out of this? And can I get beta, and can I get gamma? And in fact, I can. Because if you saw earlier, UA is equal to cosine of alpha I plus cosine of beta J plus cosine of gamma K. So all I've got to do is take this number, and if I want alpha out of it, I do, here, hang on, alpha is equal to cosine inverse of 0.394055. I don't know whether it's going to give me back radians or degrees for this, but I'm going to try to take the thing there and see if it'll figure it out. What? Okay. It doesn't give me, oh my gosh. Okay. Shoot, I'll have to use the calculator there. Okay, 0.394055. Second. 66 degrees. Okay, 66.79295 degrees. So I can do this over and over, and I can find from this I can find alpha, from this I can find beta, and from this I can find gamma. There are more times that you will walk out onto a job site carrying a ruler than you will ever carry something that measures angles. So you've got three ways of doing this. Okay, here's your three ways. You can do the cosine directions, which these are three angles. You can do this one, which is a projection, which is two angles and one distance. Or you can do this, three distances. You should be able to move back and forth between all of these because especially one of the targets is the book tends to target this one as being the end point. In other words, given this, give me that. Or given this, give me that. And that happens a lot. The other thing you can do is now that you have these three numbers, you can check for yourself. But if you take the square root of 0.394 squared, I'm just going to drop some of the digits, 0.473 squared plus 0.788 squared, you'll end up with like 1 or 0.9999999. So it was a unit vector. It was made into a unit vector. So you can do that if you want, and that's a way to check things. So it turns out this last method is given in the next section. And so what I'm going to do is roll forward a little bit so we can see that next section. Okay. Okay. Okay, so here he's doing this. Here's a typical example. Sorry for the stuff in the screen there, but here's a typical example. He has a point O and a point A. He wants you to figure this out. That's an awful looking vector. But that vector is, if you want to, this is an easy way to do it, is this. You're traveling a path. So if you want to know A, you want to go out to here. So I want to go 2 in this coordinate. Then I want to go this direction. I want to go plus 4 out the I. And then I want to go straight down. Minus 6k. So you just use the coordinates to move yourself from one point to the next one. Now, it's kind of common to write it this way, where the I, the j, and the k, but it doesn't matter. This is the vector that took place first, this is the vector that took place second, and this is the vector that took place third. So you can transverse your way down through complicated stuff just by following the coordinate direction. So somebody came to the job site, measured from here to here was 2, from here to here was 4, from here to here was 6. And they said, okay, tell me what this is. Tell me what alpha, beta, and gamma is. And so, you know, so essentially this is the section that is called, I don't know what it's called, but it's one more section ahead. So I just wanted to do all of them at one point. So here he's got a position vector, he goes through it. He goes through adding 2 positions. So if there is a rope that is tied at some point A and some point B, you may have to find this vector and this vector and then subtract the 2 of them to get the actual rope. And the reason you're going to want a rope is this. There's somebody pulling this direction in the unit direction of some R. Okay, that's a unit vector. There's somebody out here pulling like crazy, say 1,000 pounds. Guess what? What is the force vector? It's 1,000 pounds times the direction that they're pulling. So if you have that unit vector, whether you got it from here, here, or here, all you do is multiply times the tension of that rope. That gives you the force all along that rope, and you can get it back here because it's the same all along the rope. So the reason you want to find the unit vector in the direction of the rope or vector or whatever is because it's probably a rope and somebody's pulling on it. Or it might be a bar and somebody's pushing on it. So it could be one of the two. And so that's the reason you want to go through all this. You want to find those 2 endpoints, find the vector, and then end up these. So I hope I covered everything. I covered like 3 sections here, but next time we'll come in and do, if you got problems, we'll work on those problems. But if you don't, I'll come in and start pulling problems out of these 2 sections and working them. And if you are sick or you miss it, I mean, it'll be streamed and recorded. If there's something that didn't make sense to you, you could go back and watch the stream. So I know it's hard, you know, sometimes I'll be listening to a lecture and I'll fall asleep, and then pop right back up. There's studies that show, and they're kind of recent studies now, they've always shown that if you write it on the page, you remember it better. And now there's studies that are showing the reason you remember it better is because of active writing on the page keeps you awake. And so if you're taking notes and you're doing that, you're constantly keeping awake. If you're just listening to some monotone professor, pretty soon you're just like this, and you're just like, you know. And so to remember it, sometimes it's helpful to just take notes, even if they're not great notes. It does help. So, but you can take them in here. You can go watch the stream, double speed it, do whatever you want to do with it. I think you can go up to 2 times the speed on YouTube. So I'm done.